nanoHUB-U, online instruction.
So hello everyone. So we're at the end of Unit 1. So this has been an introduction to some basic concepts of transistors for those of you that are new to transistors. It's been a review of some concepts for those of you that have seen them before. What I want to do in this lecture is just to kind of summarize quickly some of the key points that you should have taken out of Unit 1, and then we'll be prepared to take the exam and to continue on with Unit 2. So these are the topics that we've discussed during Unit 1, and what I'd like to do now is just very quickly go through with some of the key takeaways from each of those lectures, remind you of what we talked about. Remember, I talked about what our objectives are, so let's not lose sight of what it is we're trying to do in this course. The first thing is to understand physically what goes on inside a transistor, how the electrons and holes flow in response to the potentials that are set up with the voltages that we apply to the terminals. But then the second important objective is to relate what goes on inside these transistors to the current versus voltage characteristics of the transistors, the currents that we would measure on the leads that are connected to the outside world. So we want to understand where typical transistor characteristics like this come from and how are they related to what goes on inside. Now, if you've taken a semiconductor course anytime in the last 20, 30, 40 years, you've learned all about this. But you've learned about how to do this in the context of very long channel lengths. What makes this interesting for us is that these channel lengths have shrunk to such small dimensions that the transport of electrons across the channel has become really interesting and much different from what it was when the theory was first developed. That's what the course is all about. To remind you, we'll be drawing these cartoon sketches of MOSFETs. So you can see the source, the drain, the gate. We have 3 terminals. We have a 4th terminal. Sometimes there's a body terminal, sometimes there isn't. We're going to be focusing on what happens with the source, drain, and gate voltages. We have a very thin insulating layer. Traditionally, it was silicon dioxide. New materials are being used these days, but it's an insulating layer that's intended to prevent DC current from flowing from the gate electrode into the silicon substrate. The critical dimension of the transistor is the channel length, L, the distance between the source and the drain, and this sets the scale of the entire device. And when the history of technology evolution is that the channel lengths have continually scaled down for 50 plus years, and that's what's made electronics more and more powerful. And then you should be used to thinking about what does this device look like from the top. If I look at it from the top, the gate has some width. You can see here the length of the gate between the source and the drain. You can see the width of the gate in this direction. You can see the contacts for the source metal and for the drain metal. And, get comfortable with looking at it both from the side view and from the top view. Mostly we're going to be drawing pictures that look like this from the side view. And remember that we are interested in modern technology, in complementary technology. So there is always a P-channel device with an N-channel device, and we have to get familiar with both. In the N-channel device, we apply positive voltages. If the gate voltage is more positive than the threshold voltage, then we have charge in the channel that can flow from the source to the drain. We can think about the positive voltage on the drain attracting electrons. They flow out. Electrons flowing out is a positive current flowing in. The complementary device is a PMOS device. We have P-type sources and drains. We apply negative voltages. If we apply a gate voltage that is more negative than the threshold voltage, and the threshold voltage is now negative, then we have positive charge carriers in the channel that can flow from the source to the drain. We can think of the negative voltage on the drain attracting the positive carriers. They flow out the drain and out the contact, and we have current flowing in the opposite direction. Most of the time I'm going to be talking about the physics in the context of N-channel transistors, but you should be able to translate that into the complementary device, and it's a good way to test your understanding of the concepts. Actually do the same thing for the PMOS device. In lecture 2, we talked about the MOSFET as a black box. So here our goal was to understand if we go in and apply voltages to these terminals, what currents flow. And we saw that the typical output characteristic looks like this. A small voltage between the drain and the source gives us a linear characteristic. The device looks like a resistor. A large voltage between the drain and the source gives us a saturation characteristic. The device looks like a current source, but not an ideal one, a current source with some output resistance. Now, if we do these characteristics for different gate voltages, we get a whole family of curves. And a typical family of curves looks like this. Increasing gate voltages give us increasing currents. So down in this linear regime, the device operates as a gate voltage dependent resistor. In this saturation regime, the device operates as a gate voltage dependent current source. Now, we can also look at the transfer characteristics. So that's the output current, the current between the drain and the source as a function of the input voltage with some specified voltage, either small or large, on the drain. And we'll get characteristics that look like this. So there is a region where there isn't much current that flows on a linear plot that looks like zero. There's only small leakage currents that flow. And then significant current flows. The current begins to flow when the gate voltage exceeds this critical voltage called the threshold voltage. Now, if I want to see what's going on in the sub-threshold regime, I have to do a log plot. So here's the same data plotted on a log plot. And if you look at a log plot, you'll see that in this sub-threshold regime, the small current is actually increasing exponentially with gate voltage. And we also see here that we have less current with less voltage. We have a translation in the horizontal dimension, which is an indication that the threshold voltage is drain voltage dependent. Okay, so we spent some time looking at those IV characteristics in detail. And in lecture 1.3, we defined some key metrics, things like on current, off current, subthreshold swing, dibble. We didn't explain much in the physics about what led to these parameters, but we defined operationally what they are. If you go into the lab, apply voltages, measure currents, you could deduce these parameters. And if you've understood those concepts, if I give you an IV characteristic, you would be able to extract those device metrics from them. Now, we also talked then in lecture 4 a little bit about just a little bit of circuit design, a little bit about how device metrics impact circuit performance. So we did that by focusing on the basic CMOS circuit, the CMOS inverter, which consists of an NMOS device and a PMOS device hooked up in series. We talked about its transfer characteristic. We tried to understand why it has the shape that it did. And we talked about things like speed, power, switching delay, and we developed some very simple expressions that really tell us about all we need in this course to know about circuit performance. The amount of energy it takes to make a 1 or a 0 is the energy stored in the switching capacitance. That's 1/2 capacitance times voltage squared. We'd like that to be as small as possible because we want to use as little energy as possible, and that means we'd like the voltage of the transistor to be as small as possible. The dynamic power, the power that occurs when we're switching the inverter or the gate, the dynamic power is proportional to the frequency. The faster we operate the chip, the more power we consume, and it's proportional to the square of the voltage. Again, another reason we want low voltage transistors if we can get them. The standby power. So one of the beautiful things about this CMOS inverter is that when it's not switching, when it's just sitting there with a 1 or a 0 on its input, ideally no power would be dissipated. In practice, there are small leakage currents, so there is some small power that is dissipated. Just a few years ago, that power was so small we could neglect it. But with the evolution of technology to the point where we have billions of transistors on a chip, that leakage power adds up, and that becomes a significant consideration. So device designers worry a lot about how do we achieve low off currents. Ideally, there should be 0 off current. In practice, we want to make it as low as possible. The speed of the circuit, or the switching delay, is determined not by the intrinsic speed of the device, about how long it takes an electron to go from the source to the drain. That's an that's an intrinsic upper limit. But in practice, it's determined by how long it takes to pump charge into the output capacitance or to pull charge out to make a 1 or a 0. And that depends on the on current. So this is the reason that device engineers, device designers want high on current, so that the circuit can operate at fast speeds, capacitors, and can be charged and discharged very quickly. And then finally, we talked about the concepts of noise margins. If you're going to do digital logic with large numbers of gates, you'll have errors. A logic 0 won't always be exactly 0 volts. A logic 1 won't be always exactly 1. But as long as they're close, as long as we have some noise margin and an input signal is small enough, then the output will be a 1. If it's big enough, then the output will be a 0. So this ability of the inverter to restore the logic levels to their proper values, even in the presence of noise, is very important for digital logic. And we showed that in order to do that, the CMOS inverter has to possess gain. And in order to possess gain, it has to have an adequate transconductance, G sub M, and an adequate output resistance, R0. So this explains the importance of some of the device metrics that we introduced in the previous lecture. And it explains why it's going to be so important for us to understand the physics that controls these so that we can help device designers design good transistors. Now in lecture 1.5, this was actually the only part of Unit 1 where we talked about physics. We presented a very simple physical picture of how a MOSFET works in terms of energy band diagrams. And this is a view of the MOSFET that is very useful. You should keep it in mind as we go through the remainder of the course. In the linear regime, we were able to look at the energy band diagram. We have a small voltage on the drain, so the conduction band in the drain is a little bit lower than it is in the source. We talked about how if we push the barrier down, we get a constant slope of the conduction band in the channel, meaning we have a constant electric field, and the device operates as a voltage-controlled resistor. Up here at high drain voltage, we pull the conduction band in the drain way down with a large voltage, but as long as there's a barrier, the device is still off, so a few electrons can hop over that barrier. That's my off current. But if you push the barrier down with a positive gate voltage, more electrons can hop over, and I turn the device on, and I get on current. So that very simple picture in terms of energy band diagrams is a good, solid physical picture of what happens. Now, you might ask then, if it's so simple, then what's this course all about? What more is there? So there are two things. The particular shape of the IV characteristic is controlled by how we manipulate these energy barriers. And that's an extremely important thing for transistor design, to be able to design the electrostatics of the transistor such that we can manipulate these energy barriers appropriately and get good IV characteristics. That's why we've devoted an entire unit to MOS electrostatics. That's our next unit. But once an electron can hop over the barrier, we have to ask how easily can it flow across the channel and out the drain. In the simplest case, it would just flow across unimpeded. That's what we call ballistic transport, and we have a whole unit later on that will be devoted to that. More realistically, it's going to encounter something. It'll encounter a defect, it'll encounter some roughness at the interface, and it may encounter a lattice vibration, and that will knock the electron in a different direction. So the electron might get knocked back to the source and not even come out the drain. It might bounce around several times and end up coming out either the source or the drain. So if there are only a few scattering events, we call that quasi-ballistic transport, and we'll learn how to understand that in the final unit of this course. If it undergoes a lot of scattering events, we call that diffusive transport. And when there is a lot of scattering in the channel, that is really the regime of traditional MOS theory, long channel MOS theory. That gets us back to the early transistors. And we'll talk about making that connection as well. Now, this is a course about how modern transistors work. And modern transistors work in the transport part of it is much different from the way transport worked in long channel devices when technology was first developed. So lecture 1.6 was a quick introduction to the traditional theory, so that we have a frame of reference, we have something that we can relate our new theory of nanotransistors to. And we developed a simple expression for the current voltage characteristics in the linear regime. We got this classic textbook expression very easily, and that's an expression that we will refer to frequently as we go through the course. In the saturation regime, we got another simple textbook expression. And as we discussed, the physics of that expression is not right. But for some reason, it appears to work reasonably well in practice. And again, we're going to come back to this frequently throughout the course and try to explain why that equation works so well and how we can do better. Then in lecture 1.7, we developed a very simple model for the complete IV characteristic of the transistor, and we called that a simple level 0 virtual source model. So the idea there was that we could connect the simple linear region expression with the simple saturation region expression with some empirical function that goes smoothly from one to the other. And we're going to continue to come back to this virtual source model throughout the course, and it will provide for us a frame of reference as our understanding of MOSFETs and nanotransistors evolves. We'll evolve this model and make it better and more physical without making it much more complicated. And that's really the interesting thing. So these are the elements that we've done in Unit 1. Have a chance to review it, make sure you're solid with all of this material. Have a look at the homework and the homework solutions that are posted. And if you are comfortable with the material, then you're ready to take the exam and ready to proceed on to Unit 2. So thanks a lot. I look forward to seeing you in Unit 2.